The question 4 says that we would like to design a sorting algorithm called tree sort. It works by inserting each data element into a binary search tree. So to print data elements in a sorted order, we traverse the tree in a certain way. Okay. So which traversal methods we use for this purpose, and what is the complexity? So maybe at first we would like to explore, right? For instance, like how does it actually work? So the idea is that you're given an array A, and let's say it contains some elements that are not yet sorted. So for example, it could be 17, 2, 5, 19, 21, 7, let's say, right? So then you're given an array, and you want to sort it. Sort it meaning that in the end, what you get is the sorted order, which is 2, 5, 7, 17, 19, 21. Regularly, you have insertion sort, you have merge sort, you have different sorting algorithms to do this. In this case, we would like to use the binary search tree to help us do this. Now, the question says, what we're going to do first is to insert each data element into the BST. So let's say we start with an empty BST, and we would like to insert this element one by one, right? So we start from 17. So where does 17 go? We put 17. Right now, the tree is empty, right? So the first one will be the root. Then we go on and process the second one. So the second one will go. So it will go to the top, to the root, and check whether 2 is the same as 17. It's not. So then it will have to go to the left or to the right. Because 2 is smaller, we go to the left. 5. 5 will start from 17 to the left, 2 to the right. So 5 will be here, 19, 21, 7. Right? So then we get a particular order, tree that looks like this. Now, once we have a binary search tree, essentially we have this already ordered, but in the tree form. What we want at the end is to return back a list that contains the elements in a sorted order. So then what kind of traversal do we do to do that? So given a BST, can we traverse it in a certain way that it would return the sorted order in terms of a list? So what are the three sort or traversals? It could be pre-order, it could be in order, or it could be post order, right? You only have 3 to choose from. So which one would it be? Then you can just try one by one, right? Even if you try one by one, you would actually get one of the answers. Now in this case, the answer is in order, right? Now why in order? Because in the case of in order, you always go to the left first, and then the parent, and then the right. And the left tends to be smaller than the parent, and the right is larger than the parent. So you visit in the order of left parent right, you essentially are going to preserve the ordering of numbers within the BST. So if you do the in order, so we start from the root, the root says go to the left first, 2 doesn't have anything on the left, so then we visit the parent, which is 2. 2 then will go on to the right, which is 5. 5 will go on to the left first, nothing on the left, so you visit itself. And then it will go to the right. Now you go to the right to 7, 7 has nothing on the left, so it will visit itself. Nothing on the right, so it starts to return. Now the left side is ready. Then we go on to 17. Then we go to the right. Again, there is nothing on the left, so we visit the parent. Going to the right, nothing on the left, we visit the parent. Then we get a sorted order, right? So this is essentially how the sorting works. So if you're going to transform it into a pseudocode, so we would write it in the following way. So for example, so we have a method called the tree sort, which takes in the array A. Then we would like to create a new binary tree, right? Let's say a binary search tree in this case. Now that we have a new binary search tree, then we can have a loop that says that for each element of A, so we're going to insert into B. Now at the end of this loop, finally, we would have a full tree that contains all of the elements of A. So then we will return the in-order traversal of A. Okay, so then what it does is to return a list of things that has been visited in the in-order way, and that's essentially the pseudocode. So then when we ask you to write a pseudocode in the midterms or in the final exam, you can write it like this, meaning that it can be sentences, but try to maintain the structure of a code and try to be as precise as possible. It doesn't have to be syntactically correct in the sense that, for example, you may miss the colon here, but it doesn't quite matter in the logic that we are trying to assess, right? So now, and if you're going to use some of the methods that are well defined in the slides, so for example, if you're going to use the traversal, pre-order, in-order, post-order, or if you're going to use the sorting, insertion, sort, merge, sort, or the searching, linear search, binary search, you don't have to reproduce the whole algorithm for merge sort, for example. Just say that I'm going to use merge sort to do this. And then my understanding is that you're going to use the same merge sort that we defined in the slides. Okay? All right. Now, this is the pseudocode. Then we are going to define what is the complexity of this. Now, certain parts are relatively straightforward. So when you create a new VST, there is nothing inside yet. So there is O1. Now, as we create this tree, we are going to insert the element one by one. This one will require a certain assumption about what we assume to be the worst case. Now, the worst case is always the case that is going to require the highest number of comparisons. And it turns out that for a tree of n elements, you can have many, many different shapes. So for example, this is one of the shapes, right? More or less, you have a height of 4 in this case. But in the worst case, your tree may not look like this. Your tree may actually look much more skewed in one direction. So for instance, let's say we are trying to insert the following numbers into the tree. Let's say, right? Now, so the root will be the first number, so that is 1. And when 2 comes in, 2 has to compare to 1. So then 2 will be here, right? And then when 3 comes in, 3 has to compare to 1 and to 2. So then 3 will be here. Now, each time we have a new entrant, we have to compare to everything else that already exists in the tree. Now, if this keeps going on, the number of comparisons that we are going to have, so 1 as the first one, there is 0 comparison. 2 as the second one has to compare to 1, so 1 comparison there. 3 has to compare to 1 and 2, so 2. 4 has to compare to 1, 2, 3, so that's a 3. And if you keep going, and supposing that at the end we end up at n, then the number of comparison at n will be n minus 1. So then if you look at the total number of comparisons that we would have to do across all these insertions, this would be 0 plus 1 plus 2 plus 3 all the way to plus n minus 1. And this number, if you do the pairing thing as before, 0 plus n minus 1, and they are n numbers, so there are n over 2 pairs. So this is going to be n squared over 2 minus n over 2, which is O n squared. Which means that in the worst case, to construct a binary search tree, it might take us O n squared to construct it. And the reason why it might take us O n squared is because for n elements in the tree, we might get actually a linear structure where every single entry will have to compare to everything else that already existed. Now, here we want to make a distinction between inserting a single node. If you just want to insert one node, then the complexity is O n, because you just need to compare to everything that is already in the tree. In this case, it's O n squared because we are not inserting one node, we are inserting n nodes. And each time, we have to compare to everything that has existed before. Right? So now this part then is ON squared. And finally, we have a third part, which is to do in-order traversal. Now the traversals, all three of them, whether it's pre-order, post-order, or in-order, they are all linear. So this is ON. So then you have three steps. The first step is O1, second step ON squared, the third step ON. So then in totality, what do you get? So in totality, you get ON squared.